Hi, everybody. It's Professor Mitchell. We're finishing up Chapter 5 already. Only 2 sections in this chapter on integers. And today we're talking about multiplication and division of integers. We'll talk about models for multiplication of integers, properties of multiplication of integers, integer division, order of operations on integers, and inequalities with integers. So one of the ways you can demonstrate integer multiplication is using a chip model. Remember that red chips represent negative numbers. So this would be an illustration of 3 times -2. To find -3 times -2, start with a value of 0 that includes at least 6 red chips. For example, 6 red and 6 yellow would be 0. And then remove 3 groups of 2 red chips. And that would leave you with 6 yellow chips. So that's an illustration that -3 times -2 equals 6. Here it is. All right. And then there's the number line model. You can demonstrate multiplication by using a cat moving across a number line. Obviously, it doesn't have to be a cat. Here are the rules for walking the number line. Always start at 0 and always start off facing in the positive direction. If the number is positive, walk forward. If the number is negative, walk backward. So here is a number line illustration of 2 times -3 equals -6. The cat starts at 0 and walks backward 3 steps and does that 2 times. And then one way, this is not the only way, to use a number line model to illustrate -3 times -2 equals 6 is just to say that -2 times -3 has to be the opposite of 2 times -3. So since we already know that 2 times -3 is -6, the opposite of 2 times -3, which would be -2 times -3, should be 6. Another way to illustrate integer multiplication is by looking at a pattern. First, find 3 times -2 using repeated addition. So 3 times -2 means -2 plus -2 plus -2, which is -6. Now use the commutative property to find -2 times 3. -2 times 3 is the same thing as 3 times -2. So that's also -6. And then to find -3 times -2, you can follow this pattern, starting with 3 times -2 equals -6. Gradually decrease the first number in the multiplication. 2 times -2 is -4. 1 times -2 is -2. 0 times -2 is 0. So we see that every time we decrease this number by 1, this number increases by 2. So if we follow that pattern, the next product should be 2, positive 2, and the next one should be 4, and the last one should be 6. Definition of integer multiplication. Let A and B be any integers. If A and B are both greater than or equal to 0, then A and B are whole numbers with product A times B. So we've already talked about how to multiply whole numbers. If A and B are both less than or equal to 0, then A times B is the absolute value of A times the absolute value of B. So for example, -3 times -2 is the same thing as 3 times 2. And if one of A or B is less than 0 while the other is greater than 0, then A times B is the opposite of absolute value of A times absolute value of B. Okay, so for example, -3 times 2 is the opposite of 3 times 2. For all integers A, B, and C, multiplication of integers is closed. As long as A and B are integers, their product is an integer. Integer multiplication is commutative. A times B equals B times A. Integer multiplication is associative. The identity property of multiplication says that 1 is the unique integer such that for all integers A, 1 times A and A times 1 are the same thing as A. Sorry, this typo is going to bother me. Let's change that to a T. Identity property. Did not notice that when I was looking this over. Okay. The distributive property of multiplication over addition holds for integers, just like it did for whole numbers. And the zero multiplication property holds for integers. 0 is the unique integer, such that for all integers A, 0 times A and A times 0 are both 0. For all integers A, B, and C, -1 times A is the opposite of A. Opposite of A times B is equal to B times opposite A, which is the opposite of A times B. And the opposite of A times the opposite of B is equal to A times B. Distributive property also holds for multiplication over subtraction. And now we come to an example. Simplify each of the following so that there are no parentheses in the final answer, starting with -3 times x minus 2. So -3 times x is -3x, and then we're going to subtract -3 times 2. -3 times 2 is -6, and of course, the opposite of 3x minus -6 is the same thing as the opposite of 3x plus 6. Next, we have x plus 4 times x minus 4. So first, we'll distribute the x plus 4 over the difference x minus 4. So x plus 4 times x minus x plus 4 times 4. Now we'll distribute the x and the 4. X times x is x squared. 4 times x is 4x. Minus 4 times x is 4x. 4 times 4 is 16. Notice this expression is still in parentheses. Change this subtraction to adding the opposite. The opposite of 4x plus 16 is opposite 4x plus -16. And now I can add these two terms together. They add up to 0 because they're opposites. And that leaves us with x squared minus 16, as you remember from your beginning algebra class. This result is called the difference of squares formula. And we'll talk about that again in a little bit. For all integers A and B, A plus B times A minus B is equal to A squared minus B squared. So now we'll use the difference of squares formula to simplify these. This is going to be faster than doing it the way we did the last one. All right, we won't really use the distributive property at all. We'll just use the formula. So for example, 4 plus B times 4 minus B should just be 4 squared minus B squared, which is 16 minus B squared. See, that's a lot faster if you know that formula. This one is almost the same, except it's -4 plus B times -4 minus B. Still has the difference of squares pattern. So this is going to be the square of -4 minus B squared. Notice that the square of -4 is still 16. So actually you get the exact same answer. When the distributive property of multiplication over subtraction is written in reverse order, as AB minus AC equals A times B minus C, and BA minus CA is equal to B minus C times A. And similarly for addition, the expressions on the right of each equation are in factored form. So this is reversing the process of multiplication. The common factor A has been factored out. Both the difference of squares formula and the distributive properties of multiplication over addition and subtraction can be used for factoring. All right, factoring is covered in intermediate algebra courses like Math C and Math 62. So you may have done this in your last math class. So let's factor each of the following, starting with x squared minus 9. Notice that fits the difference of squares pattern, which means that in factored form, it's x plus 3 times x minus 3. This one also fits the difference of squares pattern. Okay, so let's see, how did they write that formula? Did they write it in terms of A and B? Where did they do that? Yes, okay. So here's the formula, A plus B times A minus B equals A squared minus B squared. So in this problem, letter B, x plus y is playing the role of A, and z is playing the role of B. So instead of A plus B, we're going to get x plus y plus z. And instead of A minus B, we're going to get x plus y minus z. Next, we have factoring out a common factor. The common factor is x. So you sort of undistribute the x, write it out here, and then inside that leaves you with negative 3 plus 5y. All right, chip model for integer division. Here's an illustration using chips of negative 15 divided by 3. We're taking our 15 red chips, which represents negative 15, and dividing them into 3 groups. So notice each group has 5 red chips. So that's an illustration that negative 15 divided by 3 is negative 5. Definition of integer division. For all integers A and B, A divided by B is the unique integer C, if it exists, such that A is equal to B times C. So this is what I've sometimes called before division is a mystery missing number in a multiplication problem. Okay, so we can use this definition to evaluate each of these quotients. 12 divided by negative 4, that would be a number C, such that negative 4 times C is 12. And since we know that negative 4 times negative 3 is 12, that means the mystery number has to be negative 3. 12 divided by negative 4 is negative 3. Next, we have negative 12 divided by 4. Now we're looking for a number C such that 4C equals negative 12. And again, we know that negative 3 does that. 4 times negative 3 is negative 12. Therefore, negative 12 divided by 4 is negative 3. All right, then we have negative 12 divided by negative 4. Looking for a mystery number C that makes negative 4C equal negative 12. And this time we know the number 3 does that. Negative 4 times 3 is negative 12. Therefore, negative 12 divided by negative 4 is 3. How about this one? Negative 12 divided by 5. We're looking for, now remember, we're talking about integers. So we're looking for an integer C such that 5C equals negative 12. But there is no integer that does that, right? Because no integer C exists to satisfy this equation, negative 12 divided by 5 is undefined over the set of integers. So one thing this tells me is that integers are not closed under division, all right? It's definitely possible to divide two integers and get something that's not an integer. All right, throwing the alphabet into the mix. AB divided by B. All right, this is kind of a seemingly complicated way to look at it. But if we call that mystery number X, then that means that AB has to equal BX. And the only way that could happen, as long as B is not 0, is if X is the number A. So AB divided by B is equal to A. And it's likely you know a simpler way to do that. So it's probably okay for now to think of it like that. Very similar, almost the exact same problem actually. AB divided by A is going to be B, as long as A is not 0. Remember, division by 0 is undefined. All right, that brings us to ordering integers. The definition of less than for integers, very similar to the definition of less than for whole numbers. For any integers A and B, A is less than B if and only if there exists a positive integer K such that A plus K is equal to B. So for example, -5 is less than 3 because I know a number, namely 8, that makes -5 plus 8 equal 3. Okay, so that makes -5 less than 3. A is less than B, or equivalently B is greater than A, if and only if B minus A is equal to a positive integer. That is, B minus A is greater than 0. So that's a different way to say it. All right, here's a theorem. If X, Y, and N are integers, then if X is less than Y and N is any integer, then X plus N is less than Y plus N. So you likely learned this in your algebra class. We use this for solving inequalities. It says that you're allowed to add any number to both sides of an inequality. If X is less than Y, then the opposite of X is greater than the opposite of Y. And then generalizing that a little bit coming up, if X is less than Y and N is positive, then N times X is less than N times Y. So you're allowed to multiply a positive integer on both sides of an inequality. However, if you multiply a negative integer on both sides of an inequality, you have to reverse the inequality sign, remember? If X is less than Y and N is negative, then N times X is greater than N times Y. Use the theorems developed to find all integers X that satisfy the inequalities, starting with X plus 3 is less than -2. So if X plus 3 is less than -2, and we add -3 to both sides, remember the first part of the theorem says we're allowed to do that. We know that 3 plus -3 is 0, so that's going to just become X. And we know that -2 plus -3 is -5. So the integers that satisfy this inequality are all integers that are less than -5. And then opposite X minus 3 is less than 5. We'll add 3 to both sides of the inequality. All right, and then these two will add up to 0, which will leave us with opposite X is less than 8. And then by using letter B of the preceding theorem, if opposite X is less than 8, that means X is greater than -8. So all integers greater than -8 are solutions to this inequality. And for the last part of this example, if X is less than or equal to -2, find the values of 5 minus 3x. So this is sort of the opposite of what we usually do to solve an inequality. So what we're going to do is take x is less than or equal to -2. And the first thing we'll do is multiply both sides by -3. Remember, that's going to reverse the direction of the inequality symbol. So that leaves us opposite 3x is greater than or equal to 6. And now we'll add 5 to both sides of the inequality. 5 plus opposite 3x is greater than or equal to 5 plus 6, which means that 5 plus opposite 3x, which is the same thing as 5 minus 3x, is greater than or equal to 11. So if x is less than or equal to -2, that means that 5 minus 3x has to be an integer in the set 11, 12, 13, 14, etc., etc. And believe it or not, that's all there is to chapter 5. So we'll see you next time for chapter 6.